When you think of a wave, you probably picture something smooth, continuous, perfect. But what if I told you that perfection is actually an illusion? What if hidden inside the math of that simple wave is a secret fingerprint, a tiny clue pointing to a much deeper and honestly, a much stranger reality? Our story starts with an equation you've probably seen before.
Okay, so here it is, the classic wave equation. You've definitely run into this in a physics class. And it's beautiful, right? It's so elegant and powerful. It describes everything from ripples in a pond to light waves traveling across the entire universe. And it's all built on one big idea, that the stuff a wave travels through is a perfect, unbroken continuum.
And this is where things get really interesting. We are going to challenge that one big idea, that fundamental assumption of smoothness. We're going to ask a simple but totally profound question. What happens if the universe, at its most basic level, isn't smooth at all? What if it's actually made of tiny, discrete pieces?
So in this first part, it's all about shifting our perspective. We're going to see how that perfect wave from the textbook, well, it's an incredible model, an amazing approximation, but it might not be the whole truth. Think of it like a map, a really, really good map, but it's not the territory itself. Okay, this slide just lays it all out perfectly. On the left, you've got the continuum. That smooth, ideal line you can zoom into forever and ever. That's the world of classical physics, of calculus. But over on the right, you have the discrete view, a world built out of fundamental chunks or points, almost like pixels on a screen. There's a smallest possible distance. So, which one is it? Which world do we actually live in?
All right, so here's what we're going to do. We're going to take that perfect smooth wave equation and just toss it out. For now. We're going to start completely from scratch, assuming the world is discrete, and see what kind of wave equation pops out from that assumption.
This is our new foundation. It's not about some smooth fabric of reality. Nope. It's just a simple rule for how a little wobble gets passed from one point to its nearest neighbor, and then to the next one, and the one after that.
I love this analogy. Think about a guitar string. It looks totally continuous, right? But what if it were actually a chain of microscopic connected beads? How would a vibration travel down that chain? That's the exact physical picture we're building our new math on. Okay, so we've rebuilt our wave from the ground up in this chunky universe. Now, here comes the fun part, the big payoff. If this discrete view of the world is right, it should leave behind some kind of evidence, right? A mathematical clue that just wouldn't exist in the perfectly smooth version. We're going hunting for that clue.
First, before we find the clue, let's just remind ourselves of the textbook answer. In that classic continuous world, the link between a wave's frequency, that's omega, and its wave number, that's k, is this beautifully simple equation. It's clean, it's a perfect relationship. This is our control group.
But when you run the numbers for our chain of beads world, look what happens. You get that familiar first part, the c squared k squared. But then you get this other piece, a new term, a correction that depends on the wave number to the fourth power. This isn't a mistake. It's a message from the math itself.
That's it, 4. That's the secret fingerprint we've been looking for. This power of 4, this k to the fourth term, is what the source material calls the quartic correction. It is the unavoidable signature that tells you, hey, this wave is traveling through a discrete point-by-point system, not a smooth continuum. Now you might be thinking, okay, maybe that's just a fluke of this one beads on a string model. But here's the kicker. It's not. The source material shows that this correction term is a necessary, universal consequence. It's not a bug we can just get rid of, it's a fundamental feature. So let's just lock this in. What is the quartic correction? It's the first and most important mathematical sign that your smooth-looking system is secretly built on a discrete foundation. It's kind of like the ghost in the machine.
So why? Why is this correction absolutely inevitable? Well, it all boils down to 3 super simple, really common sense assumptions. First, the world is made of points. We call that discreteness. Second, points only talk to their immediate neighbors. No spooky long-distance stuff. That's locality. And third, the rules are the same everywhere. That's invariance.
And that's the whole punchline right there. You start with those 3 basic ideas, you do the math, and this k to the fourth correction term just has to pop out. It's structurally baked into the logic of the system. It has to be there. But okay, this is where it gets even cooler. The world isn't a 1D line of beads, right? It's 3D. So what happens when we move to a 2D grid or a 3D lattice? Does our little fingerprint change? Oh, yeah.
And it changes in a really, really revealing way.
So in a three-dimensional grid, that correction term gets way more interesting. It's not the same in all directions anymore. A wave traveling diagonally across the grid literally feels the discreteness differently than a wave moving straight along one of the axes, and the math shows this. The correction becomes anisotropic.
And this is the absolute best part. That complexity, that flaw, isn't a bug, it's a feature. The correction term isn't just a sign of discreteness anymore, it's a map of it. The mathematical structure of that term contains detailed information about the geometric structure of the underlying grid. It's telling you how the beads are actually arranged in space.
Okay, so let's just pull back for a second and think about the big picture here. We started with a perfect equation. We found what looked like a flaw and then discovered that flaw was actually a map to a deeper reality. This has huge implications for how we think about, well, all of science.
The source paper we're looking at just sums it up perfectly. This isn't just some abstract philosophical idea. The quartic term is a real, concrete number. It tells you exactly how much your simple, smooth model differs from the more complex, discrete reality. It literally measures the gap between the map and the territory.
And that's really what this is all about. Our most important physical laws, these gorgeous continuous equations, are phenomenally successful maps. They help us navigate the universe, but they're still just maps. And this kind of analysis, looking for the tiny corrections, the little deviations, that's how we get clues about the true nature of the territory itself.
So I'll leave you with this question to chew on. The wave equation is just one example. What other perfect, smooth laws of physics might have their own secret, structural fingerprint hidden deep inside them, just waiting for us to find it? What other clues are we missing?